Hello dear students, welcome you all. How's everyone? Okay, so session has started. Okay, so let us discuss next class, shear force and bending moment 01. So this is the first class of shear force and bending moment diagram. Okay, so first of all I will be discussing what is shear force, what is bending moment, and then we will be discussing the questions that have come in previous years. Okay, why we'll be discussing first what is shear force and bending moment? Because a lot of students have problem in understanding the concept of shear force and bending moment, and also a lot of students have problem in sign conventions. Okay, what is the sign convention of shear force, what is the sign convention of bending moment? Okay, so just a brief brush up of topics, and then we'll be moving on to ESE prelims questions. Okay, so let us start with the questions with the topic first. Okay, so first of all, what is shear force? What is shear force? So shear force is a force that will have tendency to shear away the material. Okay, what do we mean by shearing away the material? Okay, so if I am having this body, okay, this is my body, and if I'm applying some force like this, means this side I'm pulling upwards, okay, this side I'm pulling upwards, and this side I'm pushing downwards, then there will be a tendency in this cross section, that this will be sheared away. Okay, so the forces that are parallel to the cross section, they will be experiencing shearing. Okay, like this. So if I am applying some load here like this, okay, if I am applying some load here like this, and if I am applying equal and opposite load here like this, such that in vertical direction force equilibrium is maintained. Okay, whatever is the total force in downward direction, same total force in upward direction is there, but about this section, this body will have tendency to get sheared. Okay, this body will have tendency to get sheared. So after shearing, the body will look something like this. It will be sheared and it will be something like this. Okay, so whatever force that is responsible for this type of action, that is called as shearing force. Okay, so shearing force will have tendency to shear the material like this. This is called as shearing. Okay, so I hope you have understood what is the meaning of shearing. Okay, now let us come, understood or not, what is the meaning of shearing? Have you got it? Okay, so this is the meaning of shearing. Now, how to calculate the shear force? Okay, if I want to calculate shear force at this cross section, what I will do? I will do summation of all the transverse forces. Remember transverse forces. What is the meaning of transverse forces? Transverse forces are the forces that are perpendicular to the axis of the beam. Okay, so let us say this is the axis of the beam. Let us say this is the axis of the beam. Okay, now this is the axis of the beam, and these are the forces that are perpendicular to the axis. So these perpendicular forces can be either in this direction or they can be either in this direction. Okay, like this also they can be perpendicular. Okay, but we are taking xy plane. Okay, so this is x plane and this is y plane. So if my axis, if axis is in x direction, then the loading will be in y direction, and this load or this force will be called as transverse force. Okay, so understood the meaning of transverse force? What is transverse force? Okay, now if a force is acting like this, this will be axial force. Axial force means acting along the axis. Okay, axial force means acting along the axis. Now this is the transverse force. So for shearing, for this type of failure, or for this type of tendency of failure, or for this type of action, transverse force will be responsible. Axial force is not responsible for this type of failure. Okay, thank you so much. Okay, so see, so for this type of failure, axial force is not responsible. For this type of failure, transverse forces are responsible. Okay, now how to calculate how much is the shear force acting at this section? how much is the shear force acting at this section? How we can calculate? So we can calculate how much shear force is acting at this section either by doing summation of all the transverse force on this side of the section. Okay, all that summation of all the transverse forces on either right side of the section, or we can do summation of all the transverse forces on the left side of the section. Okay, now if I do summation of all the forces, then the resultant will be 0 because this body is in equilibrium. Yes or no? So when this body is in equilibrium and if I do summation of all the forces, so downward forces will be equal to upward forces, the net summation will be 0. Okay, so if I want to calculate shear force on this section, I will have to do summation of all the forces either towards the left side of the section or summation of all the transverse forces either to the right side of the section. Okay, so that will give me the magnitude of shear force. So how to calculate magnitude of shear force? Is it okay? Is it correct? Any problem in that? Calculation of magnitude of shear force? Okay, so now let us solve some very basic example so that we are able to understand even more clearly. Okay, so let us say I am having a cantilever beam like this. Okay, now on this beam, let us say a load of 20 kilonewton is acting, transverse load of 20 kilonewton is acting like this. Okay, now if I want to calculate shear force at this section, what will be the value of shear force at this section? What will be the value of shear force at this section? So shear force at this section, how can we calculate? Either doing summation of all the transverse forces on the right side of the section or summation of all the transverse forces on the left side of the section. Okay, so if I calculate transverse forces from the left side of the section, I have to calculate what is the reaction here, support reaction. But I don't know support reaction. Till now I don't know support reaction. Okay, so why take pain of first calculating the support reaction and then calculating shear force? It is easy for me to calculate shear force from this side of the section. Very good, Sayantan, very good, Sayantan. Okay, 20 kilonewton is the magnitude. Okay, so on this side of the section the force is 20 kilonewton. Okay, so the shear force will be 20 kilonewton. Correct, very good. Now let us say 20 kilonewton is acting here also. Okay, so shear force will be equal to 20 kilonewton. Okay, now let me take another example. Okay, if transverse force of 20 kilonewton is acting here, now what will be the shear force at this section? Now still the value of shear force will be 20 kilonewton only. Why? Because if I do summation of all the transverse forces to the right side of the section, there is only one force, that is 20 kilonewton. Okay, okay, no, I am not talking about bending moment, I am not talking about moment, I am talking about shear force only. So shear force is still 20 kilonewton. Okay, no, not multiplication of distance in shear force. Okay, is it clear? So in this case 20 kilonewton. Okay, now what about this case? What is the value of shear force at this section? What is the value of shear force at this section? Please tell. Value of shear force at this section? Yes, it will be 40 kilonewton because towards the right of the section I will add all the transverse forces. Okay, so shear force here in this case will be 40 kilonewton. Now tell me, what is the value of shear force at this section? What is the value of shear force at this section in this case? Now, if I apply transverse load of 50 kilonewton here, it will not impact shear force at this location. Okay, Yes, very good, correct, 0. So shear force is 0. Shear force is 0. Now on application of 50 kilonewton here, on application of 50 kilonewton here, will my shear force at this section is getting impacted? No, because I am taking from this side. Okay, I'm calculating from this side. Okay. Now, now if I apply 100 kilonewton here, then also there will be no impact. Then also there will be no impact on this section. Okay, so concept is clear for shear force. Let us do one more example. Let us solve one more example. Okay, so if this is the section, okay, and here I am having UDL of 2 kilonewton per meter over a length of 5 meter. Okay, UDL of 2 kilonewton per meter over a length of 5 meter. What will be the shear force at this location? What will be the shear force at this location? 10. Yes, very good, definitely correct answer. So shear force at this location, at this section, will be equal to 10 kilonewton. No problem at all. This is intensity. Okay, loading intensity into the length. Okay, so when they will multiply with each other, I will be getting 10 kilonewton. Okay, next example. I am having uniformly varying load. Okay, here the loading intensity is 0, and at this location loading intensity is 2 kilonewton per meter. Here loading intensity is 0, and at this location loading intensity is 2 kilonewton per meter, and this distance is 5 meter. Okay, so what will be the shear force at this section? Okay, again calculate shear force at this section. Okay, so you have given answer 5. Okay, very good. So here the shear force will be total load on this side. Okay, total load on this side. Okay, so what will be the total load given by UVL? Total load will be area of this triangle. Okay, so total load will be given by area of this triangle, and that area will be half base into height, half into base. Base is 5 meter, 5 into height is 2. Okay, so 5 kilonewton will be the answer. Okay, units will be multiplied, kilonewton per meter into meter. So meter and meter will cancel out. I will be getting kilonewton only. Okay, yes, very good. So this is clear. Now I think shear force, there is no doubt in shear force. Let us move on to bending moment. Okay, so let us see bending moment. Bending moment. Okay, so bending moment is that moment which will bend the beam. Okay, so if my beam is like this, just a minute. If my beam is like this, okay, and if I have applied a moment, and that moment which is responsible for the bending of the beam, that will be bending moment. Okay, so what is the, how do you calculate moment? How do you calculate moment? Moment is simply force into perpendicular distance. Moment will be equal to force into perpendicular distance. Force into perpendicular distance. This will be the moment. And what will be the bending moment? Bending moment will be summation of all the moments, summation of all the moments on either side of the section, on either side of the section. Either side of the section means that, suppose if my beam is like this, suppose if my beam is like this, okay, and there is one moment like this, there is one force like this, okay, and I have to calculate moment here, okay, and let us say there is one moment like this here, m dash, okay, and here also we will be having some support reaction, let us say r. Here also we will be having some moment m double dash, okay. So if this is my section, let us say I am designating this as xx, this is my section, okay. So at this section, if I want to calculate bending moment, how will I calculate bending moment? Bending moment will be summation of moment on either side of the section. So I can do summation of moments on this side of the section also. So all the moments on this side of the section, or I can do summation of moments on this side of the section. So I can do summation of moments on either side of this section, okay, not both the sides. If I do summation of moments on both the sides, then it will come out to be 0, because this beam is in equilibrium, so summation of moments will always be 0. So I don't have to do summation of moments on both the sides, okay. I have to do summation of moments on either this side or this side, okay. So how to do summation of moment? If moment is given, this is directly moment, no need to multiply any distance, this is directly moment is given, okay. So in moment you don't multiply distance in order to calculate moment, moment in itself is moment only, okay. So this moment m plus, so bending moment at this section, bending moment at xx will be equal to m plus force into this distance, let us say this distance is x, so it will be p into x. Clear? Okay, so if I calculate from this side, it will be m plus p into x, right? Now this I have done without considering the sign convention. Sign convention, let me tell you sign convention also, okay, so that there is no confusion. So sign convention is, if the force is tending to bend the beam in this way, tending to bend the beam in this way, tending to bend the beam in this way, then it is positive, okay. And if the force is tending to beam, or if the moment is tending to bend the beam, force or moment tends to bend the beam in this way, then it will be negative, then it will be negative, okay. So here what we are seeing, that we are getting compression on top surface, compression on top surface and tension on bottom surface, okay. So this fiber is getting slightly stretched, bottommost fibers are slightly getting stretched and topmost fibers are getting slightly compressed, okay. So at the top, if we are getting compression and at the bottom we are getting tension, then it is positive, and this is also called as sagging bending moment, sagging bending moment, okay. And on the contrary, if I am getting tension on top and compression on bottom, this is called as hogging bending moment, and it will be negative, okay. Now if I consider this moment is tending to bend the beam in this manner or this manner, tell me. This moment, just look at this moment alone. So this moment is tending to bend the beam in this manner, sagging, or it is giving hogging bending moment, tell me. If this is the moment, here bending moment will be in the sagging manner or hogging manner, tell me. So in case of any confusion, what you do, just take an imaginary beam, hold it here at this section, and in whatever manner this moment is trying to rotate, you rotate it, okay. So you will see at the top you are getting tension, and at the bottom you are getting compression, and it is getting bent like this, okay, like this part is getting bent like this, so it will be negative. So I will put minus sign here, okay, minus sign here. Now because of force P also, it will be bending something like this only, okay. So it is bending like this, okay. So this is also hogging bending moment. So when it is hogging bending moment, sign convention will be negative, okay. So because of this moment and because of this force, because of both of them, we are getting hogging bending moment only. So bending moment will be minus m minus px. Is it clear? Any doubt? Are you having any doubt? Okay, so, and if I calculate from this side, because of this R, because of this support reaction, I will be getting sagging bending moment. Okay, why? Because R will be having tendency to bend the beam like this. Because of R, beam will be bending like this, sagging. Okay, so R will give me positive bending moment. Okay, M double dash will give me negative, because M double dash have tendency to bend this beam like this. M double dash has tendency to bend this beam like this. Okay, and M dash also is giving me negative. Okay, so M double dash, M dash, both are giving negative, that means hogging bending moment, and R is giving sagging bending moment positive. Okay, clear? So sign convention is also clear, I think. And sign convention for shear force, sign convention will be like this, that if shear force is giving clockwise rotation, if the combination of these two forces, or if this force is giving clockwise rotation, this force is also giving clockwise rotation, if both the forces are giving clockwise rotation, it will be positive. And if the force is giving anti-clockwise rotation to the element, anti-clockwise rotation, it will be negative. Okay, so if these forces are giving clockwise rotation, it will be positive. If these forces are giving anti-clockwise rotation, it will be negative. Shear force will be negative. Is it clear? Right? So let's move on to questions now. Okay, questions. So first question, ESE 1995, for the coplanar concurrent system of forces as shown in the given figure, the system will be. Okay, so coplanar and concurrent. Concurrent means all the forces are meeting at a single point, and coplanar means all the forces are lying in this plane only. Okay, all the forces are lying in one plane only. These are coplanar forces. Okay, and concurrent means all the forces are meeting at a point. Okay, so just give me what will be the answer. Come on, fast. Tell me the answer. Okay, so see, F1 force is acting like this, F2 force is acting like this. Okay, both these forces are different magnitude. Okay, and then F3 force is acting like this, and we have to find out the magnitude of F3 such that equilibrium is maintained. So what do you think? At the given angle, can equilibrium be maintained? Equilibrium cannot be maintained. Why equilibrium cannot be maintained? Because if I do summation fx equal to 0, if I do, so here I will be getting F3 cos 45 degree, that means F3 by root 2 should be equal to 20 kilonewton, right? F3 by root 2 should be equal to 20 kilonewton. If I do summation fx equal to 0, now if I do summation fy equal to 0, I will be getting F3 sin 45 degree is equal to 10 kilonewton. F3 sin 45 degree is equal to 10 kilonewton. F3 sin 45 degree means F3 by root 2 is equal to 10 kilonewton. So F3 equal to 20 root 2 kilonewton and F3 equal to 10 root 2 kilonewton. Is it possible that two values of F3 are there? F3 is having two different values. Is it possible? No. So that's why it will not be in equilibrium, whatever be the magnitude of F3. It will not be in equilibrium. Okay, if I do vertical equilibrium so that F3 is equal to 10 root 2. So vertical equilibrium is maintained, but horizontal equilibrium will be disturbed. And in order to maintain horizontal equilibrium, F3 should be 20 root 2. So if I do F3 is equal to 20 root 2, then vertical equilibrium will be disturbed. Vertical equilibrium will be disturbed, right? So there is no value of F3 such that equilibrium can be maintained. Okay. Okay, next question. Assertion and reason. Bending moment in a beam is maximum at a section where shear force is 0. Okay, so in SFD BMD, one more concept is there, that partial derivative of bending moment or rate of change of bending moment will be equal to shear force. Okay, so rate of change of bending moment is equal to shear force, or slope of bending moment diagram will be equal to shear force. Okay, also rate of change of shear force will be equal to loading intensity. Rate of change of shear force will be equal to loading intensity, right? So slope of shear force diagram is equal to loading intensity. Slope of bending moment diagram will be equal to shear force. Okay, so bending moment in a beam is maximum at a section where shear force is 0. So if I put shear force is equal to 0, I will be getting dm by dx is equal to 0. Now dm by dx, if it becomes 0, this is the condition of maximum bending moment. So in order to find maxima or minima, we put this condition that dm by dx is equal to 0. So if I want to find out the value of maximum bending moment, or if I want to find out the value of minimum bending moment, I use this condition. So bending moment in a beam is maximum at a section where shear force is 0. This is correct. This is absolutely true. Next, reason. Shear force at a section is given by the rate of change of bending moment. They are asking opposite, na? Shear force at a section is given by rate. Shear force at a section is given by rate of change of bending moment. Yes, correct, true. And this is the reason why this is happening. This is explaining it properly also. Okay, so both the statements are true, and it is the correct explanation of this also. So correct answer will be option A. Any doubt? Let's move on to next question if there is no doubt. So parallelogram law of forces. Now earlier this question 25 years back, 30 years back, this type of questions were asked in strength of materials. Okay, 20 years back, 25 years back, these type of questions were asked in strength of materials. But nowadays these questions are introduced in a separate subject, new subject that is introduced, engineering mechanics. So these type of questions you will study in engineering mechanics. Okay, so we will not be dealing too much in this type of questions, but since it has come in the slide, so let us solve it. But this will be covered by Aishwarya sir in engineering mechanics. Okay, the parallelogram of law of forces states that if two forces acting simultaneously at a point be represented in magnitude and direction by two adjacent sides of the parallelogram, their resultant may be represented in magnitude and direction by. Okay, so if there are two forces like this, okay, and these are represented by two sides of parallelogram, so I'll have to make parallelogram also. So if this is my parallelogram, so magnitude and direction is represented like this. Okay, I am representing by parallelogram. So what will be the resultant of these two forces? What will longer side of the two sides? No, resultant will be given by this, na? This will be the resultant. So resultant will be given by diagonal. Okay, shorter side of the other two sides, diagonal of the parallelogram which does not pass through their point of intersection. No, it will pass through the point of intersection. Okay, so diagonal for the parallelogram which passes through the point of intersection. So correct answer will be option D. Okay, so if these are the two forces, they are represented by sides of parallelogram, the resultant will be diagonal of the parallelogram that passes through the point of intersection of these two forces. Correct? Okay, so option D is correct. Next question. Match list 1 type and position of load on cantilever with list 2 shape of moment diagram for cantilever and select the correct answer using the codes given below the lists. Okay. Type and position of load on cantilever. So we are having cantilever beam. We are having a cantilever beam. So type and position of load on cantilever, it is given in list 1, and shape of bending moment diagram is given in list 2. Okay. So if my cantilever beam is carrying linearly varying load from 0 at its free end and maximum at the fixed end. So 0 at the free end and maximum at the fixed end, like this. Okay. So my cantilever beam is carrying load like this. So what will be the shape of bending moment diagram? So one thing you must know, that shear force diagram will be 1 degree higher than loading diagram, and bending moment diagram will be 1 degree higher than the shear force diagram. So if this is a straight line, okay, that means it is linear. So loading diagram is linear in this case, shear force diagram will be parabola, and bending moment diagram will be cubic parabola. Cubic parabola. Okay. So for this shear force diagram will be parabola and bending moment diagram will be cubic parabola. Okay. So it will be cubic parabola. So A will be having 3. Treatment 3. Okay. Next, subjected to uniformly distributed load. So if my cantilever beam is subjected to uniformly distributed load, what will happen? If my cantilever beam is subjected to uniformly distributed load like this, so this load throughout the beam is constant. Load is constant. So 1 degree higher will be linear. So shear force diagram will be linear and bending moment diagram will be parabola. Bending moment diagram will be parabola. Okay. So bending moment diagram will be parabola. So B will be having 1. Okay. Carrying concentrated load at its free end. So if I am having concentrated load at the free end, if I am having concentrated load P at the free end, shear force diagram. So shear force diagram will be constant. My shear force diagram will be constant. Shear force diagram will be constant and bending moment diagram will be linear. Okay. So shear force diagram will be constant and bending moment diagram will be linear, or I can say triangle. Okay. Bending moment diagram will become triangle. So this will be 4. Whose free end is subjected to bending moment? So if my free end is subjected to bending moment, then shear force everywhere is 0 and bending moment diagram will be constant. Bending moment diagram will be constant. Constant means it will become rectangle. Okay. So constant means it will be rectangle. So 3142 will be the correct answer. 3142 will be the correct answer. 3142. Option C is the correct answer. Option C is the correct answer. Clear? Right? Next, the bending moment diagram of the beam shown in figure is. Okay, so here we are having a beam. Just a minute. Okay, here we are having a beam, and on this beam a load is applied on the beam, but load is applied indirectly. Okay, load is directly not applied on the beam directly. Here one bracket is connected and on this bracket the load is applied. Now because of this we have to find out the bending moment diagram. So first let me transfer this load on the beam. Okay, it is actually indirectly coming onto the beam. So let us directly transfer this load on the beam. So if I transfer this load directly onto the beam, how will I transfer? Let me draw the beam first. So this is my beam, simply supported beam. Okay, now here I am having hinge support, here hinge support, here I am having roller support. Okay, so load is coming onto this bracket and this bracket is transferring this load onto the beam. So this 2 kilonewton, what is the point on the beam at which this 2 kilonewton is transferred? This 2 kilonewton is transferred on the beam at point M. So this 2 kilonewton is transferred on the beam at this point M. Okay, so two kilonewton will be transferred here. Now this beam this load here, in this original case, it is acting at some distance from M. Because of this distance, it is producing a moment also. Okay, because of this distance, it is producing a moment also. Okay, so when I've transferred this load here, I have not considered the moment that was coming. So because of this distance, the moment was also coming. So I have to consider that moment also. So 2 into 1, force into perpendicular distance. This is the perpendicular distance. 1 meter is the perpendicular distance. So because of this distance, I'm getting 2 kilonewton meter moment is acting here. Okay, now 2 kilonewton load is acting and 2 kilonewton meter moment is acting here, right? Now I have to draw the bending moment diagram. So let us first calculate the support reactions. Okay, so how to calculate support reaction? This distance is 2 meter. Now this distance is 3 meter. So distance is, let me write down, distance is 2 meter. This distance is 3 meter. Okay. So here the support reaction will be 2 into 3 by 5, 2 into 3 by 5. Force into opposite length divided by total length. Force 2 kilonewton into opposite length divided by total length. Okay, plus, no, it will be minus. Because of this, it will be minus. So because of force, I have calculated this support reaction, and because of moment also I will be calculating. Because of moment, I will be getting M by L. Moment is 2 divided by length, so minus 2 by 5. So 2 into 3 by 5 minus 2 by 5, so 4 by 5. This will be equal to 4 by 5. Okay, and here support reaction will be 2 into 2 by 5, 2 into 2 by 5, because 2 kilonewton into opposite length divided by total length, 2 into 2 by 5 minus M by L. So no, it will be plus 2 by 5. So 2 2s are 4, 4 plus 2 6, 6 by 5. This will be 6 by 5. So if I add 4 by 5 plus 6 by 5, I will be getting 10 by 5. 10 by 5, that means 2. So total downward load will be 2 kilonewton. Total upward reaction will also be 2 kilonewton. Okay, clear. So this support reaction is 4 by 5, this is 6 by 5. Okay, now because of this, I will be getting positive bending moment, and from here also I will be getting positive bending moment. From here, 4 by 5 into 2, that means 8 by 5, 8 by 5, 8 by 5, that means 1.6. Okay, so 1.6 kilonewton meter will be here, and 2.4 will be from here. 1.6 and 2.4, 1.6 and 2.4. So yes, 1.6 and 2 kilonewton meter is this distance. So if I add 1.6 and 2, a minute, 6 by 5 into 3. Yes, 6 by 5 into 3. 6 3s are 18 by 5. 18 by 5 means 2.6. Yes, so it will be, sorry, 3.6. It will be 3.6, not 2.6. 3.6, yes. So 1.6 and 3.6. So this will be 3.6 kilonewton meter. Okay, so correct answer will be option A. Any doubt? Any doubt? You can ask me if there is any doubt, and if there is no doubt, let's move on to the next question. Okay. Next question. The shear force diagram and bending moment diagram for a beam are shown in the given figures 1 and 2. So this is the bending moment diagram, this is the shear force diagram. The corresponding loading diagram would be, now there are some rules that when shear force is suddenly changing its magnitude, there is a sudden change in magnitude of the shear force, there will be either support reaction or there will be point load. So there can be two cases here. Either point load is there, or support reaction is there. So at these two locations, either point load or support reaction. Okay, for a beam, and we are not given which type of beam. Is it cantilever beam or simply supported beam or whatever? That is not given. But one thing is for sure, that at this location, there is 1 kilonewton, 1 ton of upward force, concentrated upward force is acting, and at this location 1 ton of, again, at this location again 1 ton of upward force is acting. Okay, so at both these locations 1 ton of upward force is acting. Now from bending moment diagram, it is clear that at this location there is not a hinge. Okay, here moment is also coming. At this location moment is also coming, and when at this location a moment is also coming, that implies that this is a fixed support. Okay, so this will be a fixed support. And on this fixed support there is support reaction 1 ton in vertically upward direction, and 4 ton meter is the moment. Okay, so moment is negative, that means here it is like this, 4 ton meter. Okay, this is the support moment and support reaction, vertical support reaction. Here there is concentrated moment. At this location concentrated moment is present. Concentrated moment. And here, since it is coming in downward direction, here we will be having 1 ton of force. Okay, this is 1 meter. So 1 ton force into 1 meter distance, 1 ton meter is the moment here, and here will be it is sudden drop of 1 ton meter. So moment of 1 ton meter is acting. 1 ton meter is acting, and it is giving negative bending moment. Negative moment is there. So because of this, we are getting drop. Okay, sagging bending moment. So this will be giving sagging bending moment. So this is the beam. Okay, so if I calculate moment here, so 1 into 2 plus 1. 1 into 2 plus 1. So this should be 3 ton meter, na? Why 4 ton meter is coming? Okay, let us see. Okay, one more thing. Yes, one more thing we forgot, that this bending moment diagram, this is shear force diagram. Yes. So no UDL can be there. There can be no UDL. Okay, so basically I think here 2 ton meter is written wrong. This actually it should be, this value should be 2 ton meter. This value should be 2 ton meter. Okay, in question it is wrong. This value should be 2 ton meter. This difference should be 2 ton meter. Okay, so 1 ton meter up to here, and this difference 2 ton meter, then it will become 3 ton meter here. Okay, so this will be 2 ton meter. 2 ton meter. Now if we calculate here, 4 ton meter will be coming. So 1 ton force into perpendicular distance is 2 meter. So 2 ton meter from here plus this 2 ton meter. So 2 ton meter because of this force. The moment of 2 ton meter will be because of this point load. Okay, and plus 2 ton meter because of this moment. Okay, so resultant will be 4 ton meter. So in question it was wrong. It should be like this. So this will be the correct answer. Correct answer will be option B. Understood? Any doubt? Next question. Just a minute. A simply supported beam is loaded as shown in the given figure. So this is the simply supported beam. It is loaded as shown in the given figure. The bending moment at E would be. So we have to calculate the bending moment at B. Okay. Now, first of all, we have to calculate support reactions. Now, can you calculate support reaction RA and RB? RA and RB. Support reaction will be same. Okay, because of this moment, whatever support reaction is coming here, equal and opposite support reaction will be coming because of this moment. Okay, because these moments are acting opposite to each other. So whatever support reaction will be produced by this moment, equal and opposite will be produced by this, because magnitude is also same. So because of these two, support reactions at both of the ends will be cancelled out. Because of these two moments, support reactions will be cancelled out. So support reactions will be because of these only. I am talking about support reactions, not about bending moment or shear force. Okay, that scenario is different. Now, if I want to calculate support reaction, for support reaction, because of this and because of this, they both will be producing equal and opposite. Equal and opposite cancel out. Okay. So, yes, the support reaction RA will be equal to 2 into 1, 2, 3, 4. 2 into 4 by 5, 2 into 4 by 5 plus 4 into 3 by 5, 4 into 3 by 5 plus 2 into, how this, 1, 2, just a minute. So this will be 1 meter, this will be 1 meter, this will be 1 meter, this will be 1 meter. Okay. So RA, support reaction RA will be, see, force into opposite length by total length, RA. Okay, so if I calculate RA because of this 2 ton, okay, alone, then I calculate RA because of this 4 ton alone, then I will calculate RA because of this 2 ton alone, and then I will add all of them. So this is the principle of superposition. By this I can find value of RA. So RA will be equal to 2 into 3 by 4, 2 into 3 by 4 plus 4 into 2 by 4, 4 into 2 by 4 plus 2 into 1 by 4, 2 into 1 by 4. So that will be equal to 2 3s are 6 by 4. Oh, sorry. So 4 will be getting common, 6 plus 8 plus 2. So 16 by 4, that will be 4 ton, 4 ton. And RB will also be 4 ton. Okay, so we have found out the support reactions. Now we can calculate the bending moment at point M. Bending moment at point E. Why this M is written? Bending moment at point E. So we have to calculate bending moment at point E. So how to calculate? Either we can do summation of moment towards the right side of the section, or we can do summation of moments either to the left of the section. Okay, so summation of all the moments to the right of the section. How to do? So summation of all the moments to the right of the section, bending moment at point E will be equal to, so RB, because of RB we will be getting sagging bending moment. So RB into 2 meter, so 4 into 2 minus 2 into 1 minus 2 ton meter. So 4 to 8, 8 minus 4, that will be 4 ton meter. So bending moment at E will be equal to 4 ton meter. 4 ton meter, and it is coming out to be positive. Positive, that means it will be sagging bending moment. So correct answer will be option D. So correct answer will be option D. Clear? Next question. Which one of the following statements is correct? Okay, so let us see which one of the following statements is correct. Shear force is the first derivative of bending moment. So dm by dx is equal to V. We know this. So this is the shear force and this is the first derivative of bending moment. So first derivative of bending moment is equal to shear force. This is correct. Which one of the following statements is correct? Option A is correct. Shear force is the first derivative. Shear force is the first derivative of intensity of load? No. Load intensity on a beam is the first derivative of bending moment? No. Bending moment is the first derivative of shear force? No. Okay, so option A is correct. Okay, next. Assertion: the maximum bending moment occurs where the shear force is either 0 or changes sign. So we know that first derivative of bending moment is shear force. dm by dx is equal to v. Okay, so maximum bending moment occurs where shear force is either 0 or changes sign. Now if shear force is changing sign at any point, shear force is changing sign, so either it is becoming from positive to negative or it is becoming from negative to positive. So in both the cases, either from positive to negative or from negative to positive, at the point at which it is changing sign, it is becoming 0. Okay, so at the point at which shear force is changing sign, it is basically becoming 0 only. Okay, so if my shear force is 0, if I put this shear force 0, then at that point my bending moment will become maximum. When dm by dx is equal to 0, that means bending moment is maximum. So the maximum bending moment occurs where the shear force is either 0 or changes sign. This is true. 100% correct. No doubt at all. Next, reason. If the shear force diagram line between the 2 points is horizontal, the bending moment diagram line is inclined. But if the shear force diagram line is inclined, the bending moment diagram is a parabola of second degree. Yes, this is also correct, because rate of change of bending moment is equal to shear force, or from here we can say that slope of bending moment diagram is equal to shear force. Slope of bending moment diagram is equal to shear force. What does this mean? That if shear force diagram between 2 points is horizontal, that means if shear force diagram is horizontal line, shear force diagram is horizontal line, that means shear force is constant. Shear force is horizontal line, that means shear force is constant. When shear force is constant, that means slope of bending moment diagram is constant. Slope of bending moment diagram is constant, that means bending moment diagram line is inclined. Yes or no? Okay, so if shear force diagram between 2 points is horizontal, shear force diagram between 2 points is horizontal, that means shear force is constant. And if shear force is constant, then slope of bending moment is constant. Slope of bending moment is constant means bending moment diagram line is inclined. So this is correct. Okay, next. If the shear force diagram is inclined, if shear force diagram is inclined, that means it is a straight line. It is a straight line. Shear force diagram line is a straight line. Now if shear force diagram line is a straight line, that means slope of bending moment diagram is changing linearly. Slope is changing linearly. Okay, that means the bending moment will be parabolic. Okay, so bending moment, if shear force is varying with x to the power 1, if shear force is varying with x to the power 1, that means bending moment m will be varying with x to the power 2. That is only when partial derivative of bending moment will give shear force. Okay, so if I do partial derivative here, it will become linear. So if this is linear, then this will be parabolic. Okay, so if the shear force diagram is inclined, inclined means slope line of constant slope. Okay, it is inclined line of constant slope. Okay, that means bending moment diagram is parabola of second degree. So this is also correct, but this is not explaining this. This is true individually, this is also true individually, but this is not the explanation of this. So this is also true, reason is also true, but this is not the correct explanation. So correct answer will be option B. Option B will be the correct answer, right? Hello Ashwani, how are you? Next. Oh, this question looks little bit difficult. Let us see what is asked. So if the loads and reactions of the beam shown are as given in the following figure. So we are given some loads. So 2 ton load is given, 5.87 ton, 3.464, 4.24, and so many loads are given. Okay, so some axial loads are also given, some transverse loads are also given. Axial loads, transverse load, both are given. So the thrust diagram on the section of the beam taking tension positive will be, so we are asked thrust diagram. Thrust diagram means thrust is axial thrust. That means axial force diagram. So we have to draw axial force diagram only. So we will ignore all the transverse forces. We will ignore this. No need to look at this. We will ignore this. No need to look at this. We'll ignore this. No need to look at this. Okay. We will ignore this. No need. Okay. We will ignore this. We'll ignore all these transverse forces. Okay. So we will ignore, when we'll ignore all the transverse forces, we'll have to consider this horizontal force, this horizontal force, this horizontal force, and this horizontal force. All these horizontal forces we have to consider. Okay. Now, if I have to draw the thrust diagram or axial force diagram taking tension as positive, so just tell me in portion AC, what will be the value of tension force? What will be the value of axial thrust? What will be the value of axial thrust in this region? Axial thrust, if you consider this section, at this section, if we do summation of all the forces to the left, so this is 3.222 ton, this is going towards the left, and it is a tension force, so 3.222 ton will be the tension. Okay, so in this region it will be positive 3.222. okay, positive 3.222 ton force. Now let's come to this section. At this section, so 3.222 going in that direction, 3.464 is coming in this direction. So this is giving compression and this is giving tension. This is giving compression, this is giving tension. Okay, so 3 and 3 will be cancelled out. Net resultant will be compression because this is greater. Net resultant will be compression because this is greater. So this compression minus tension, net resultant will be compression, it will be negative. What will be the magnitude? 3.464 minus 3.222, it will be 0.242. So 0.242 negative. Okay, next. Here 4.242. If I consider this section, okay, now let us consider from this side. It will be easy. So here there is no axial force, it will be 0 in this portion, 0 in EB portion, and here 4 ton is positive, so I'll be getting positive 4 ton. Okay, so here in this part, AC part positive 3.222, in CD part negative 0.242, in DE part positive 4 ton, and in EB part 0. Clear? So let us see. 3.222 positive, 0.242 negative, 4 positive, and here in this part 0. Okay, so this is the correct answer. Option A is the correct answer. Let us see other options also. So here they have reversed everything. Okay, sign convention they have reversed. Here in this portion it should be 0, and in this portion it should be, so they have changed. Okay, so this option is correct answer. Okay, let's move on to the next question. In next question, match list 1 type of beam with loading with maximum bending moment value. Okay, so here what will be the maximum bending moment value? Maximum bending moment value will be coming at this point. This is a cantilever beam and uniformly varying load. Now for cantilever beam and uniformly varying load, zero load is here, loading intensity is 0 here, and loading intensity is W here. So what will be the maximum bending moment value? Maximum bending moment value will be force into perpendicular distance. Okay, so M max will be at this location. So total force will be area of this triangle, half base into height. Half base into height means WL by 2 into perpendicular distance. So centroid will be at L by 3 from here. So L by 3 multiplied, so we will be getting WL square by 6. So M max in this case will be WL square by 6. So WL square by 6, 2. Okay, so for A, 2 will be the correct answer. Here, what will be the M max in this case? M max in this case, what will be the value of maximum bending moment? Maximum bending moment location will be here, again at this location. Okay, so total load into centroidal distance of the load. Okay, so total load will be WL WL, okay, and centroidal distance, so this is constant loading, so centroidal distance will be L by 2. Centroidal distance will be L by 2. So WL into L by 2, I'll be getting WL square by 2. WL square by 2, right? So WL square by 2, 3. So for B, I'll be getting 3. Next, here. So the total load will be divided into total load acting downwards. It will be half of the load will be supported by this, half of the load will be supported or resisted by this support. Okay, so total load will be WL by 2, triangular. Okay, triangular loading is there, so total load is WL by 2. So WL by 4 will be resisted by this, WL by 4 will be resisted by this support. So here WL by 4 and WL by 4. Now if I want to calculate maximum bending moment will be coming at this location, at midpoint. Okay, so if I calculate bending moment at this location, how can I calculate? So it will be coming because of two forces. One is the support reaction and other is this total loading, this. So because of this I'll be getting Mx will be equal to WL by 4 into distance is how much? L by 2. L by 2, right? Minus this loading will also be WL by 4. Okay, total load was WL by 2. This loading will also be WL by 4. So WL by 4 into, but now perpendicular distance will be here, perpendicular distance will be 1/3 of L by 2. This distance is L by 2. This distance is L by 2. And centroid of this triangle will be 1/3 of L by 2. 1/3 of L by 2 means L by 6. L by 6. Okay, so this is L by 2. And this is 1 by 3 into L by 2. So L by 6. So WL square by 8, 1 minus 1 by 3. So 2 by 3. So WL square by 4 3s are 12. WL square by 12 will be the correct answer. So for this, we'll be getting WL square by 12. If you wish, you can writing also. Okay, Ratlo. If you wish, you just remember. Bye. Good night, Ashwini. Okay, so WL square by 12. Now for this WL square by 8, it is, everyone knows this will be WL square by 8. So WL square by 8 is 4. So D 4 will be there. So 2 3 1 4. 2 3 1 4. 2 3 1 4. 2 3 1 4. Correct answer is option C. So if we just calculate for these two, then also we could have found the answer. But since we are practicing, so while practicing, let us solve each and everything, right? Okay. Now next question. For the beam shown in the given figure, the maximum positive bending moment is equal to negative bending moment. So value of L1 is. So when this also you have to remember, you can learn it, okay, and I can directly say that option is D, just remember it, but I'm not doing because we will solve it. Okay, we want to solve it, we are practicing. Okay, so here maximum negative bending moment should be equal to maximum positive bending moment. Maximum negative bending moment should be equal to maximum positive bending moment. So the bending moment diagram, shape of bending moment diagram will be something like this. Shape of bending moment diagram is like this. Okay, so here what is the value? Something. Here we are having a value, here we are having a value, here we are having some value. Okay, so at these three locations some value is there. Okay, so because of symmetry, this value and this value, they both are equal, and this value might be different. But in the question they are saying that maximum negative bending moment should be equal to maximum positive bending moment. Okay, so whatever value of bending moment we are getting here, same value should be coming here. So for that case, what should be the value of L1? So L1 will be L by 2 root 2, but let us calculate. So here at this location, let us say this maximum negative bending moment is M1 and this is M2. Okay, so value of M1 will be equal to W L1 square by 2. I'm talking about magnitude only. Okay, no need to consider what direction or the sign convention. Okay, I'm just considering the magnitude. Okay, so magnitude here M1 will be equal to W L1 square by 2, and M2, magnitude of M2 will be equal to, it will be maximum positive. So let us find out this support reaction. This support reaction will be equal to W into, total load divided by 2. Total load will be W L1 plus L1 whole upon 2. So it will be W L1 plus L by 2. This will be the value of support reaction. Okay, so I have to calculate bending moment M2 at this location. So bending moment M2 at this location will be R into this perpendicular distance minus W into this length square by 2. So R into perpendicular distance, reaction into perpendicular distance. What is the perpendicular distance here? This total length is L, this total span is L, so this perpendicular distance will be L by 2. So R into L by 2. So R into L by 2 minus W into this distance square by 2. W into this distance is L1 plus L by 2 whole square by 2. So minus W L1 plus L by 2 whole square by 2. What is the value of R? Support reaction R is W L1 plus L by 2. So W L1 plus L by 2 into L2 R into L by 2. This is L by 2. R into L by 2 minus W L1 plus L by 2 whole square by 2. Okay, so this M1 should be equal to M2. Okay, so W L1 square by 2 should be equal to W L1 plus L by 2 into L by 2 minus W by 2 L1 square W just a minute, W L1 plus L by 2. Yes, W L1 plus L by 2 whole square by 2. So L1 plus L square by 4 plus L1 into L. Okay, now some terms will be cancelled out. W by 2, W by 2, W by 2. These are cancelled out from both the sides. Okay, so let us solve further. L1 square will be equal to L into L1 plus L square by 2 minus L1 square minus L square by 4 minus L into L1 L. Okay, so L into L1 and minus L into L1, this will get cancelled out. L square by 2 minus L square by 4, this will become L square by 4, and L1 square will come this side, this will become 2L1 square will be equal to L square by 4. Okay, so from this we can say that L1 square is equal to L square by 8. From this we can say L1 is equal to L by 2 root 2. L1 is equal to L by 2 root 2. Okay, so this is the correct answer. Correct answer is option D. So this is, I have told you how to solve this question, but in examination you will not get so much time that you can solve, so you can remember this result. Okay, you can remember this result. Is it clear? Okay, now let's move on to next question. Understood this one? Any doubt in this question? No doubt. So let's move on to the next question. Consider the shear force diagram shown in the given figure. So this is the shear force diagram, and in this shear force diagram, at this location we are getting sudden change in the value of shear force. At this location we are getting sudden change in the value of shear force. At this location we are getting sudden change in the value of shear force. At this location we are getting the sudden change in value of shear force. So at these locations where there is sudden change in the value of shear force, there will be either point load or there will be support reaction. Okay, either these two things will be there. Okay, so here whatever is the support reaction or point load, it is acting in upward direction. It is acting in upward direction. So here it will be acting in upward direction, and it will be, the magnitude will be of 14 ton. 14 ton magnitude. Okay, from here to here, no change in shear force. So no change in there is no loading. Okay, zero change in shear force, so zero loading. At this location there is downward load of 14 plus 4, 18 ton. Downward load of 18 ton. Okay, from here there is a linear change in shear force. When there is linear change or linear decline in the value of shear force, then there is UDL. And what is the value of UDL? UDL will be dV by dx. Change in shear force divided by length in which it is changing, that will be the intensity of loading. Minus sign indicates that downward loading will be there. So change in the value of shear force, change in the value final minus initial. Final value is minus 16 minus initial value is minus 4 divided by length 8 meter. 8 meter, it will be equal to minus W. Okay, so minus 16 plus 4, that means it will be 12. 12 by 8, 12 by 8 minus 12 by 8 minus 1.5 is equal to minus W. So W is equal to 1.5 ton per meter. Okay, so minus 1.5. Here it will be upward direction, upward point load. Point load is in upward. Okay, so 16 plus 9, 16 plus 9 is 25. So 25 ton. Okay, here 3 ton in downward direction, 3 ton, and UDL is acting in this portion also. So UDL is acting throughout, and the value is 1.5 ton per meter. Okay, let us calculate what is the magnitude of UDL here also, because in some cases it might happen that different magnitude of UDL is acting here and different magnitude of UDL is acting here. Okay, so if slope of this is same, if slope of this line is same, then same value of UDL. If slope is different, then different value. Okay, so let us not measure the slope like this. Okay, we have to check the slope by values, numerical values. Okay, so change in shear force here. Final minus initial. Final value is 3 minus initial value is 9. Length is 4 meter is equal to minus W. Okay, so 3 minus 9 is minus 6. Minus 6 by 4 is equal to minus W. It will be minus 1.5 ton. So minus minus will get cancelled out. Okay, so we'll get W is equal to 1.5 ton per meter. Okay, so it is same in both the parts. So let us see what is the correct answer. So here it will be 14 ton, here will be 18 ton, here will be 25 ton, and here will be 1.5 ton per meter, 3 ton. Okay, so this is the correct answer. Option A is the correct answer. Now, no need of solving so much. We could have done it right away just by looking at the options. We could have eliminated the options. See, here in this region there is no UDL, gone. Okay, in this region there is no UDL, gone. We can see that here we are having sloping line, so there should be UDL. Here there is sloping line, so there should be UDL. Okay, so in this region there is no UDL, in this region there is no UDL, and here UDL is present, but in this region UDL is not present. So exactly opposite, here there should not be any UDL and here there should be UDL. So without any calculation also this question could have been done, right? without any calculation also this question could have been done. Okay, but I have told you that in case there are some confusing options, okay, so how can you solve it, right? Clear. Next question, match list 1 type and position of force on cantilever with list 2 shape of bending moment diagram. So if cantilever beam is carrying, similar question is repeated, no? Similar question is repeated, right? Earlier also this type of question has been asked. Okay, so linearly varying load from 0 at its free end and maximum at the fixed end. 1996. Let us see. Previously also it has been asked. Similar question. Here maximum bending moment value. See. 1995 and 1996. Same question is repeated. Right? Same question. So no need to solve it again. Carrying linearly varying load from 0 at its free end and maximum at the fixed end. So bending moment diagram will be cubic parabola. SFD will be parabola and BMD will be cubic parabola. Cubic parabola. Okay, so A option 3. Subjected to uniformly distributed load. So SFD will be triangular, and BMD will be parabola. 1. So 1 for B. Carrying concentrated load at free end. SFD is rectangle. And BMD is triangle. Okay, so BMD is triangle. 4. D, whose free end is subjected to bending moment. When free end is subjected to bending moment, SFD is 0, shear force diagram is 0, and BMD is rectangle. BMD is rectangle, so 2. 3142. 3142. Correct answer is option C. Option C is the correct answer. Clear? Let's move on to next question. In a beam AB, support A is hinged and support B is on rollers as shown in figure below. The directions of the reactions at A and B will be. Okay, so this is an interesting question. Can you solve it? How you can solve this question? So 2-ton force is acting here. Okay, now here at B, the support is inclined at 45 degree to the horizontal. Okay, support is inclined at 45 degree to the horizontal. Now the support reaction at B will be like this, RB. This will be like this, perpendicular to the direction of roller. Okay, perpendicular to the direction of roller, this will be RB. Okay, now if RB is like this, it will be having components, one vertical like this, okay, one horizontal like this. Now in order to counter this horizontal component, at this support reaction also there will be one horizontal component, yes or no? One horizontal component will be coming in this direction, and in order to counter this horizontal component, equal and opposite horizontal component should be here. Then only this beam will be stable. And obviously because of this 2-ton, some vertical reaction will be here, some vertical reaction will be here, like this. So resultant at this support will be like this. Resultant RA at this support will be like this. Okay, so RA resultant at RA will be going like this. Resultant at RB will be going like this. Let us see. RA in this direction, wrong. RA here, RB here, wrong. RA here, RB here, like this. This is correct. RA like this, RB like this, wrong. Okay, so correct answer will be option C. Option C is the correct answer. Clear? Let's move on to next question. If the area under the shear curve of a beam between the 2 points x1 and x2 is K. Okay, so let us say this is a beam. Any loading is there. Let us say this is the shear force diagram. let us say this is the shear force diagram, okay, and let us say this is the bending moment diagram. Bending moment diagram. Okay, now there are 2 points x1 and x2. So let us say this point is x1. So this is shear force diagram, this is bending moment diagram. So this is shear force diagram. Now this is point x1, let us say this point is x2. Okay, so the area under the shear curve for a beam between 2 points x1 and x2. So this is point x1, this is point x2. Area under this is k. This is the area. Okay, this area is k. Then the difference between the moments at the 2 points x1 and x2. Difference between the moments. Let us say moment here is m1 and moment here is m2. So we have to calculate the difference between moments m2 minus m1, that we have to calculate. Okay, now we know dm by dx is equal to v. This we already know. What we will do, we'll move this dx here. Okay, so let us take any general section, any point. At this point, let us say this width is dx, this width is dx. Okay, here the width is dx. At this, let us not write here. Let us choose any 2 points like this. Okay, and the distance, not any 2 points, let us choose a section and a very small distance, small elemental width we are taking dx. Dx is the very small elemental width, and here the value of shear force is v. The value of shear force is v. Okay, so we know that dm will be slight change in bending moment between these 2 points. Dm, what is the value of dm? Slight change in bending moment between these 2 points. Dm will be equal to v into dx. What does v into dx represent? Here v is representing shear force at this section. Na? V is representing shear force at this section. So v into dx, that means the area of this small strip is represented by small change in bending moment here. Now if we integrate this from point 1 to point 2, so from point 1 here we are having bending moment m1, and at point 2 we are having bending moment m2. So from point 1 to point 2, if I integrate this, okay, I will be getting integration of bending moment as m, that we'll see. Okay, now from here to here I will be getting, from x1 to x2 I will be getting entire area of this. What is the entire area? Entire area is k. So integration of bending moment is m, and it is varying from m1 to m2, and here it will be area of shear force diagram between x1 and x2, area of SFD between x1 and x2, and that will be equal to k. It is given in question, and here I am getting m2 minus m1, m2 minus m1. m2 minus m1, that means what is the change in bending moment between these 2 points? It is equal to the area of shear force diagram between these 2 points. Right? Hello, Ashwini. So the question is, difference between the moments at the 2 points x1 and x2 will be equal to option A, k. K is the correct answer. Clear? Let's move on to next question. Type of beam with type of loading and maximum bending moment formula. For this maximum bending moment formula, same questions are repeating again and again, you can see. Okay, so here the maximum bending moment is WL square by 12, here WL square by 8, WL square by 8, here WL square by 2, and here WL square by 6. Okay, we have already calculated all these values some time back. So WL square by 12, 6, 2 and 8. So WL square by 6 2, A2, WL square by 2, 3, B3, WL square by 12, 1, and this will be obviously then 4. Okay, so 2, 3, 1, 4, 2, 3, 1, 4. Correct answer will be option A. Option A will be the correct answer. So if you practice so many questions, okay, slowly and slowly you will see that your speed is increasing automatically just by solving the questions. Okay. Next, bending moment may be defined as the algebraic sum of the moments of all the force on either side of the section. This is the basic definition of bending moment. Correct? True. Okay. Next, reason: the rate of change of bending moment is equal to the shear force at the section. This is also true. This is also correct, but it is not the correct explanation. Okay, this is not the correct explanation. So both are individually true, but R is not correct explanation of A. Correct answer will be option B. Clear? Let's move on to next question. Just a minute. Okay, next question. Which one of the following statements is not correct? Bending moment diagram can have a change of slope only under transverse load. If there is no transverse load, will bending moment diagram change the shape? When there is no transverse load, no transverse load, what does that mean? Will there be any change in shear force? Hi, Ashu. If there is no transverse load, will there be any change in shear force? No change in shear force. That means shear force is constant. So that means shear force is constant. And when shear force is constant, that means slope of bending moment diagram is constant. Slope of BMD is constant. That means when there is no transverse load, shear force is constant and slope of bending moment diagram is constant. That means a bending moment diagram can have change of slope only under a transverse load. So when there is bending moment diagram can have a change of slope only under a transverse force. So this is correct. This is correct. Okay. Next, the bending moment is maximum where shear force is 0. So we know that dm by dx is equal to v. So if shear force is 0, bending moment diagram will be maximum. So this is also correct. Okay. Next, non-linear bending moment diagram is possible only in the distributed load regions. So wherever there is distributed load, so at that point shear force diagram will be linear. Okay, linear, and bending moment diagram will be parabolic, or there will be non-linear bending moment diagram. So this is also correct. Okay. Every support of a continuous beam, the maximum value of negative bending moment in the span are experienced. So if I am having, just take for example continuous beam like this. Okay, so if I am having continuous beam like this, so this is my loading, and okay, so bending moment diagram will be like this. Bending moment diagram will be like this. Okay, so in between the spans wherever there is middle of the span, so near about the middle of the spans we will be getting positive bending moment, and at the supports we will be getting negative bending moment. Okay, please repeat. Which question, which point? Sayande, please tell which point you want to know again, which point you want to be repeated. Okay, so at every support of a continuous beam, the maximum value of negative moment in the span are experienced. So if we talk about the middle supports, maximum negative value is experienced, that is true. But here they are talking at every support, at every support, at every support. Are we getting maximum negative value of bending moment at this support? Are we getting maximum negative bending moment value at this support? No. Are we getting maximum negative bending moment value at this support? No. So at these two supports we are getting zero bending moment. Okay, so this statement becomes wrong. At every support of a continuous beam, maximum value of negative bending. So at the interior supports we will be getting the maximum negative bending moment, but not on the exterior supports. Okay, so because of this they have written every support, this becomes incorrect. This becomes incorrect. So that means correct answer will be option D. Correct answer will be option D. Okay, so let us finish this class now, and because time is up, and we'll meet in the next session. So today is Thursday. This class is repeated every Tuesday, Thursday and Saturday. So every Tuesday, Thursday and Saturday. Okay, sorry, I forgot. Today is Saturday. So today is Saturday. So we'll meet next Tuesday. Okay, so this was the first class of SFD BMD. Remaining class will be covered one by one. Okay, so next class will be on Tuesday. So please be on time, 9 p.m. to 10:30 p.m. 9 p.m. to 10:30 p.m. we'll be having classes regularly. Okay, clear? So let's meet up in the next class on Tuesday. Till then, bye bye. Take care.